Hey there! Welcome back to the National Solar Observatory for the next instalment of our Eclipse webcast. In previous webcasts, we've covered the layers of the atmosphere. We've talked about the layers that are going to be visible during the solar eclipse, specifically the chromosphere and the corona. We've also talked about how the sun is magnetic and how it has an inherent magnetic field that ends up being the source of a lot of its activity. So today we're going to delve a little bit more into that solar activity and just figure out the difference between solar flares and CMEs and prominences and filaments. We also have a very special guest, Dr. Alex Young from NASA's Goddard Space Flight Center, who's going to give us the scientist's perspective on space weather and on solar activity and why it is important for us that we study these phenomena in the first place. Okay, so let's get started. Space weather is a term that's becoming more and more popular every day. You may be hearing about it in the news, you might even be hearing about it coming from the government. And this is because it's something that's actually quite important to us, not only from a scientific perspective, but also from an everyday life perspective. Space weather is a phenomenon that's caused by the sun that can have an effect on things like GPS signals. So while it can have effect on our cell phones and on the reliability of your applications to get you from one place to another, it's also something of very significant interest to, say, the Department of Defense or to commercial airlines. So what exactly is space weather? So on the Earth, we have weather systems that affect our everyday life. We look at the weather channel to see if it's going to be raining today or if it's going to be sunny or if there's a hurricane forecast. And scientists can use mathematical models to predict what the likely weather is in a particular place on the Earth at any given time. Likewise on the sun, we try to use solar activity and things that we can see occurring on the sun to try and predict what the sun is going to do in the near future. We have a long way to go yet. We're nowhere near as close as Earth weather predictors are, but we're making progress. So last month we talked about the fact that the sun is magnetic. It has an inherent magnetic field that in its simplest form looks a little like a bar magnet, but is generally much more complex than that, with big loop structures that come out from its surface and magnetic field structures that start at the surface of the sun and actually reach all the way out into space. Scientists can study the changes in these magnetic behaviors to try and predict what the sun is going to do. So we have observations of what the sun has done in the past, and we use those observations to try and identify features or behaviors that the sun might have that will help us to predict that a solar flare or a coronal mass ejection might be coming. So it's very important to know that solar flares and coronal mass ejections happen all the time. They happen multiple times a day during the peak of solar activity, and even during solar minimum, they happen on a semi-regular basis. So they're not something that in general we need to be concerned about. Now, every few hundred years, we do get a monster solar storm that could potentially have quite a hazardous effect on Earth. One of the biggest concerns that we have is that it can induce electrical currents in our electricity grids on the ground that might completely blow electricity grids all over the world. This actually happened as recently as 1989, where the entire city of Quebec lost its electrical power as a result of a solar storm overwhelming its electricity grid. So the study of space weather began in 1859 with what's commonly known as the Carrington event. The Carrington event was a very, very large geomagnetic storm or solar eruption that hit the Earth, and it sent magnetometers, which are instruments for measuring magnetic fields on the Earth, off the charts. There was aurora seen almost as far south as the equator. There was aurora observed in Cuba, for example, which is unheard of. Normally the aurora is only seen close to the north and south poles. So this Carrington event storm really initiated the study of space weather and the fact that the sun, even though it's a celestial body and it's something that we depend on for our light and heat, can also have a negative effect on our everyday life. And it's something that we need to understand and need to appreciate and be prepared for in the event of a similarly large solar storm. So when we talk about space weather and solar activity, what exactly are we talking about? We've mentioned the word CME or coronal mass ejection, and we've mentioned the word solar flare. But what are they and how are they connected together? Are they the same thing? Are they dependent on each other? The easiest way to think about solar flares and coronal mass ejections, or CMEs for short, is that they're two sides to the same coin. So the way I like to think of it is like a hot air balloon rising from the surface of the Earth up into the atmosphere. So in this case, here's our hot air balloon, and our hot air balloon represents a blob of material that's suspended in the corona in what we call a coronal loop. And these loops are generally large. They're larger than the diameter of the Earth, and they're filled with hot million-degree gases that are trapped inside of these loops. So here we have our hot air balloon that represents our coronal loop, tethered to the sun using magnetic fields. So in this scenario, our magnetic fields are represented by the ropes that are holding our hot air balloon down onto the ground. What happens if our tethers get really wound up, or if there's a lot of stress put on them, so they start to fray and they start to snap? That's our solar flare. So a solar flare is a release of energy, and this is seen generally as a flash of light. So a solar flare doesn't ever really leave the sun. It's the sudden release of energy that results in a very quick and very powerful flash of light. Now, as our tethers begin to fray and they begin to snap, our hot air balloon begins to rise. And in this case, the hot air balloon represents our coronal mass ejection. So this is literally an ejection of coronal material. It also includes magnetic fields, but it's the stuff, it's the material that leaves the sun and propagates out through space. So now we have our hot air balloon that has been released by its tethers, that is rising up into the atmosphere, which represents our coronal mass ejection. And as you can see, our flare is over. The release of energy happens at the beginning, where the tethers are broken and they're frayed, and that's the solar flare. And then as our hot air balloon is rising away from the surface, and that's the coronal mass ejection, or the ejection of coronal material and magnetic field. And it's these coronal mass ejections, or CMEs, that become the geomagnetic storms. So they're called geomagnetic storms if they are approaching the Earth. So the Earth has a magnetic field of its own, and these CMEs are filled with magnetic field also. And so the interaction between the magnetic field in the coronal mass ejection and the magnetic field of the Earth is what causes the Earth's magnetic field to reform and to inject energy into the Earth's atmosphere. And this is actually what causes the aurora borealis and the aurora australis. So this is why we get aurora. It's as a result of geomagnetic storms interacting with the Earth's magnetic field, causing it to peel back and fold back on itself and inject energetic particles that travel along magnetic field lines to the North and the South Pole. And as those particles interact with the atmosphere, they get rid of their energy. Their energy has to go somewhere. And in this case, they deposit their energy in the atmosphere, in the atoms in our atmosphere. And so those atoms then start to glow to dissipate the energy. So different atoms at different heights in the atmosphere give off light of different colours. So we get beautiful reds and purples and greens moving like sheets in the upper atmosphere as the northern and southern lights. Okay, so let's go back to the sun, which is where we're going to try and keep our focus today. Today we're interested specifically in coronal mass ejections, because if we get really lucky during the solar eclipse, there may be a coronal mass ejection. I said earlier that scientists are working to try and predict space weather and solar activity, but it's really very difficult to do with any advance warning. So I've discussed the differences between solar flares and coronal mass ejections. And the other two terms that are very frequently thrown about are prominences and filaments. And during the solar eclipse, again, a prominence is something that it's very likely that you'll be able to see. So that first of all, the difference between prominences and filaments are none. They're exactly the same thing. So scientists observed prominences and observed filaments at different times, and they did not realize that they were actually the same phenomenon because they look very different. The only difference is that a prominence occurs on the limb of the sun, but if we see it on the disk of the sun, so looking at the face of the sun, then it's called a filament. They're generally blobs of cooler gases suspended in the atmosphere by magnetic fields. So because they're in the atmosphere and because they're cooler than the gases behind them from the surface, on the surface they appear dark. They're absorbing the light from the material behind them. However, when they're on the edge of the sun, or on the limb of the sun as we call it, there's no light from the material behind it to absorb, and so it appears bright. So that's the confusion between a prominence on the limb or a filament on the disk. Fingers crossed, on eclipse day there will be some prominences that we'll be able to see, especially once the sun is completely eclipsed by the moon. And even not on eclipse day, if you have the opportunity to look through a solar telescope, you will be able to see solar prominences off the edge of the limb of the sun. So to recap, today we've talked about coronal loops, which are large regions of hot gases suspended in the atmosphere. We've talked about filaments and prominences, which are the same thing, and they're large regions of cool gas suspended in the atmosphere. We've talked about solar flares, which are the sudden release of light and energy, and we've talked about coronal mass ejections, which is an eruption of material and magnetic field that flies through space. So in case you're worried about coronal mass ejections, it's worth remembering that coronal mass ejections are ejected in all directions away from the sun. So around the sun there's 360 degrees, and of those 360 degrees the Earth only takes up half a degree. So even when there is a large event, there's no guarantee that it will actually interact with the Earth. So next up, for our eclipse tip section, we have a game for you. This is the solar flare and coronal mass ejection game. We mentioned earlier that the chances of a coronal mass ejection actually hitting the Earth is pretty slim. So in this game, we have a slingshot, which represents a solar flare. We have a sponge ball or a Nerf ball that represents our coronal mass ejection, and we have these stress balls that are in the shape of Earths that represent the Earth, obviously. And so the game is to try and launch Nerf balls at the Earth and to try and hit the Earth.
Coronal mass ejections, or CMEs, are large blobs of charged solar material and magnetic field that get ejected away from the surface of the sun. Solar flares are different from coronal mass ejections, although they do often happen at the same time. Any solar flare that occurs on the disk of the sun that's facing the Earth can reach the Earth, since light is emitted out in all directions pointing away from the sun. Coronal mass ejections are directed outward from the surface of the sun in one direction. The CME will only hit Earth if it's in the direct path. So the Earth takes about half a degree of the full 360 degrees surrounding the sun, so this is a little bit less likely. Both solar flares and CMEs can have a big impact at Earth. They can also have a damaging effect on GPS and communication satellites, rendering these unreliable. Okay, for this activity, you're going to need a slingshot, safety goggles, foam balls as well there, stress earth ball, scissors, some tape, paper clips, Sharpie, cup, the nice lip on it. If you're doing the activity with magnetism, you're going to want some of these small neodymium magnets, about 8 of those, as well as a nice Alnico bar magnet. For this activity, we're going to be shooting some coronal mass ejections at the Earth, in this case, the foam earth ball, as well as a little satellite, which I have printed off from some clip art on the internet. You could draw one if you don't have access to a printer, and we're going to set it up on the cup. So now we want to modify our foam balls into coronal mass ejections. So it'll be clear what they are. So I'm just going to write CME on here, and if you want to, you might want to put some little pluses and minuses on here just to let people know that this is made out of charged particles. Let's see what we got. If you want to do the magnetic version of this activity, you're going to start with your foam earth and your long Alnico bar magnet. So what I did was just in the bottom, I cut a small hole, and then because the foam is soft, you can pretty much just put your magnet right through there. Make sure the north end of your bar magnet is at the North Pole here, just for reality's sake. So next, we're gonna need to make a magnetic coronal mass ejection. So start with your regular non-magnetic coronal mass ejection and your stack of little 1/4-inch neodymium magnets. So we are going to affix these to the outside of the CME so that they stick to our earth. And with your scissors, you're gonna go ahead and just cut a small hole in the surface of your coronal mass ejection. And then you can take your little magnet and just stick it in there. If you have super glue, you can try that, but I went ahead and just used some tape here, small amount of tape, and just cover up that magnet with the tape so that it stays in place. So if you do that enough times, you'll have a little CME that looks like this. This one has 8 of those small neodymium magnets inside of it. So for the magnetic version of this activity, you're going to want to affix your bar magnet and earth combination to the wall or some other convenient surface. And then you'll have your participants use the magnetic coronal mass ejection and attempt to connect to the earth. So here we go.
So hopefully that will be a helpful way of engaging kids during your eclipse event, or helping them to understand the differences between a coronal mass ejection and a solar flare in the future. All right, next up we have special guest Dr. Alex Young from NASA's Goddard Space Flight Center, who's joining us today to talk about the scientist's perspective on coronal mass ejections and solar flares. Over to you, Alex.
My name is Alex Young. I'm a solar astrophysicist at NASA Goddard Space Flight Center. So what I want to talk about is solar activity. The most important point is magnetism. It's really all about magnetism. The sun is a giant magnet. Now, it's not a solid magnet. It's actually kind of like a liquid or a gas. It's a plasma. So it has the properties of a liquid and a gas, but it has this special property that it's electromagnetic. That is, the stuff in the sun, the fourth state of matter, interacts with magnetic fields. In this case, we're really interested in the number of sunspots, because those are the magnetic fields that are all twisted up, bunched together. They become extremely concentrated and they become buoyant and they float to the surface. Sunspots contain a lot of energy. So you can imagine, magnetic fields are kind of like rubber bands. That is, they have tension, when you move them back and forth, when you stretch them. So if you take a rubber band and you start to twist it, eventually it gets all knotted up. And it gets so knotted because you're building up energy inside of it that eventually that energy's got to go somewhere. The knotting takes care of that for a while, but at some point, so much energy that the rubber band snaps. And when the rubber band snaps, in this case it releases heat, and magnetic fields do something quite similar. They release heat and they move material when they release energy. They do it through a process somewhat different. It's called magnetic reconnection. And it's basically when the magnetic fields get all twisted up, they very violently and quickly restructure themselves, going from being knotted and full of energy to a much simpler state. And when that happens, it happens in a very explosive fashion. And we call this magnetic reconnection. Now, it's important on the sun. It actually turns out it's important through the entire universe. It happens everywhere. It happens around the Earth, causes the aurora. It happens at other planets. It happens at comets, but it also happens at things like black holes, neutron stars. So it's It's a really important fundamental process. But in this case, it's especially important for the sun because it's how the sun sheds its energy, how it releases this magnetic energy. So once that rubber band or magnetic field suddenly releases its energy, it accelerates particles. They follow the magnetic fields. And it turns out that when the energy is released in the solar atmosphere, some of the particles stream down the magnetic field very quickly, and they get to the lower part of the solar atmosphere where it's much denser, and they slam into it. And it turns out this is actually kind of like what happens in a particle accelerator, something like you would have at CERN or Fermilab. Particles slam in together at incredible speeds, near the speed of light, huge amounts of energy. And when they do that, they release heat, they move material, but they also release light. And that happens very quickly. In a flash, we get light through the entire electromagnetic spectrum, from microwaves and radio, visible light, all the way to extreme ultraviolet, X-rays, and gamma rays. So every wavelength of light. That flash, that sudden release of energy when these magnetic fields reconfigure, is called a solar flare. So it's actually quite simple, and a lot of times people kind of confuse solar flares with another part of space weather called a coronal mass ejection. So you have all that material, it's releasing light suddenly, but also remember I said that material moves. So some of that material has moved down, creating our solar flare, but some of that material moves up, and it moves up really fast. Not quite as fast as those particles traveling near the speed of light, but still, from our eyes, pretty darn fast. Millions and millions of miles an hour, millions and millions of kilometers an hour. Flies away from the sun, and this is a lot of stuff. Billions of tons of solar material. When this big blob of stuff floats away very fast, it carries magnetic field with it. So now you have the flash, the solar flare, and the blob of solar material and magnetic field flying away from the surface. And that is called a coronal mass ejection. And a lot of times you'll see pictures of the sun with this stuff flying away, and people will call that a solar flare. That's actually not the solar flare. The solar flare is the really simple flash. It's the coronal mass ejection. The flare, when that flash goes off, it takes 8 minutes for that light to get here. And in the most cases, the camera is actually somewhere near Earth. So it turns out that when we see that flash, it's actually here already, the light from the solar flare. The coronal mass ejection, on the other hand, takes anywhere from about 16, 17 hours to several days, depending on how fast it is and how big it is. Now, there's one other part of solar activity related to solar space weather, and that's called a solar energetic particle event. Now, what happens is sometimes if the magnetic field is just right at the sun, particles don't just go down to the solar surface, but they actually go up into space. And that creates what's called a solar energetic particle. But that's not the only way that a solar energetic particle is created. The other way is that CME, coronal mass ejection, is traveling through space, and it's plowing through space. And space is not empty. It's full of particles and electric and magnetic fields. And it plows that stuff up, kind of like a snow plow. It accelerates the stuff that's pushing so quickly that just like the flare doing it, the CME is doing it as it's traveling through space and creates a solar energetic particle. So we actually have two different ways in which we see these and the ways in which they're created. So those three things are solar space weather. So we've talked about these types of space weather: the flare, the CME, and the solar energetic particle. So the next question is, how do scientists study this? What do you do to actually study this? And there's a couple of things you can do. You can use telescopes on the ground. We have a lot of very sophisticated, really amazing ones. We have new ones that are in the works, like the DICAS telescope. It's not always easy to image very energetic light, not quite as easy as your normal camera. So we put spacecraft into space, all different kinds. We put what we call imagers. That tells us, for example, where the flare is happening, where the CME is coming from. But then we actually follow nature, because nature makes a really cool kind of observation for us called a total solar eclipse. In that case, the moon blocks out the disk of the sun and allows us to see the extended atmosphere of the sun, called the corona, this wispy structure, very faint, but that's actually where the magnetic fields are defining all of the structure that you see. And that's where energy is being released that's producing solar flares, coronal mass ejections, and solar energetic particles. So we do something similar. We create what's called a coronagraph. We take a telescope, in this case usually just one that looks in visible light, or we call that white light, and now we look towards the sun, but we put up a disk on a little arm and we block this disk of the sun out, because again, it's so much brighter than the outer part. And that now allows us to see the outer corona, and when a CME leaves the sun, and it kind of, a lot of times, depending on how the direction you're looking at, it can look sort of like a light bulb or like a big croissant leaving the sun. And you see that structure travel away because we're using a coronagraph. Now, the difficulty is we can't do as good a job as nature, because nature has so much more length to work with. It can perfectly block out the sun for the most part. When we do that with a coronagraph, we actually get effects around the edge that mean that we can't actually image quite as close to, we can't block the sun right at the edge of it like the total solar eclipse from nature does. So we can only see about maybe 2 or so solar radiuses away from the sun. The problem, of course, is it turns out that all of that action again really is happening down at about 2 solar radiuses. So that is one of the advantages now of actually going back to the ground and looking at the sun with a total solar eclipse. In the visible light, as that light is getting to the ground, we can see this special area, this region where all this stuff is happening, all this energy is being released, only using nature. That is why scientists are super, super excited, because August 21st, 2017, we have a total solar eclipse. Normally, when you look at a total solar eclipse, you get about maybe 1, 2, 3 minutes of time. But if you take the same observations all along that path, then you end up getting observations of the corona for about 90 minutes. And that is really exciting, because that is what we need to really understand what's going on. We need to see the dynamics. We need to see things happening, things changing. And hopefully, if we get lucky, a coronal mass ejection will happen during that total solar eclipse, and we'll see it with one of our ground-based telescopes. And that's what we really would love to see during this total solar eclipse, to see the magnetic fields changing, to see the corona, and to see where all the cool stuff is happening. So I hope that everyone really gets a chance to enjoy this eclipse. It is an amazing event, something that many people describe as being life-changing. So if you can, try to make it to the path of totality, and if you can't, still enjoy the eclipse, because everyone in the North America, Central America, and a good portion of South America is going to at least get to experience a partial eclipse. And there's also lots of ways that you can observe it online. But just make sure that you check out all the safety literature, you do this safely, and if you plan an event, you take the proper steps to really make sure it's a safe and fun event for everyone. Now you can find out a lot more at www.nso.edu/eclipse 2017 or eclipse2017.nasa.gov. Have a great year. Enjoy that eclipse. It's going to be fantastic.
Thank you, Alex. It's always really helpful to hear from a scientist's perspective of why these things are important and how they can have an effect on our everyday life. As always, if you would like to hear more from us, please feel free to get in touch. You can find us on Twitter at NatSolarObs. You can get us on Facebook at National Solar Observatory. And we now have an Instagram account at National Solar Observatory on Instagram.